Yeah, so thank you so much for the invitation. It's really nice to be here. It's really nice to see some of the work that you do in the 5-minute talks that we had yesterday. I enjoyed it a lot, so thanks very much. And I'm very happy that today and tomorrow I can present one line of research that I've been thinking about in the last few years, and we have some more experts in the room as well, so thinking of the people from the Ghent group, maybe also people from other places that I haven't talked to yet. Yeah, it would be nice to talk to you as well about current developments, but the course, of course, is intended for everyone who hasn't heard about better-quasi-orders or ordinal analysis so far. So please do ask a lot of questions. I will try to explain everything reasonably self-contained way, but it's also very easy to lose people by using notation that maybe you use differently or so. So please do ask whenever something is unclear. It would really be great to keep everyone on board. And also my slides are available on the website of the Schrödinger Institute. If you look at the schedule, below my first talk in the schedule, there's the full set of slides. It will also be a mix of slides, not that many actually, and proofs on the blackboard. So if you're using a tablet, you could, for example, download the slides and then insert pages in between to write down the proofs or something like that. So that's why I wanted to upload the slides beforehand. The talk has 3 parts. So in the first part, I will motivate and give the definition of better-quasi-orderings and show at least one bigger application. And this might take all of the 2 lecture slots today, because it's really quite a technical definition. So if you haven't seen it before and I would just write it down, then it might be hard to see what it's good for. So I'll try really and build towards that and maybe even show how Crispin Nash-Williams, who introduced the notion in the first place, might have arrived at the definition. And then in the second part, which might be the first lecture tomorrow, I'll give a quick introduction into ordinal analysis, mainly of Peano arithmetic. So some people may have seen that, but I really want to do that from scratch as well. So please ask many questions in that part also, because I think it's a method that hasn't maybe been used that much in reverse mathematics. And I hope to show you that it can really come in to produce some nice results, and that it's maybe worth taking it in your toolkit if it's not there already. So that will be the third lecture probably. And then in the third part, which is the last lecture, I'll show how the 2 come together to produce a nice result of reverse mathematics, I would say. Good. So better-quasi-orderings, the first thing to say is probably what a quasi-order is. It's a relation that is reflexive and transitive. It does not need to be antisymmetric. If it's antisymmetric, then it's called a partial order. And one example that you could keep in mind is maybe the embeddability relation or some embeddability relation on graphs. That's reflexive. Each graph can be embedded in itself by the identity embedding. It's transitive. If you can embed one graph into another and then you have an embedding into a third graph, then you can compose the 2 embeddings. And it's not necessarily antisymmetric, at least if you think of infinite graphs, because you can imagine quite well, I think, that of 2 infinite graphs, one can be embedded into the other without the 2 being the same or isomorphic. Right? You can always get antisymmetry, if you like, by taking a quotient. So you can say that 2 objects are equivalent when each can be embedded into the other. And then you quotient that out, and then you have antisymmetry, and then you have a partial order that for our purposes does essentially the same as the quasi-order. So you may assume antisymmetry whenever you like, but in applications, like for these infinite graphs, for example, it's often more natural to consider quasi-orderings rather than making them partial. And we will see the following subsequently stronger notions about these quasi-orderings. So the weakest notion that I want to consider is well-foundedness, something that we all know very well. That's very useful because you can do induction. Along well-founded relations, you can do recursion. But then we will see that there is also reason to strengthen this notion in the case of quasi or partial orders. And what will come out of this is two notions called well-quasi-ordering and better-quasi-ordering. Maybe one thing to say is that in the case of linear orders, these all coincide. And then we speak of well orders. And if you haven't heard of well or better-quasi-orderings, then that may well be why this is the case, because they are all the same in the linear situation. And so there's no need to introduce them as long as you are mainly interested in linear orderings. And so you can also see this entire endeavor as trying to find the right extension of the notion of well order to partial orders, where not all elements are comparable. And maybe well-foundedness is not quite the right notion to consider, because it doesn't address at all the issue of incomparable elements, right? And the other two notions will address that issue. Let's jump right into the first of the new definitions here, well-quasi-ordering. So this is a definition and a theorem, because we have four equivalent conditions that you could all take as definition for well-quasi-orderings, and the theorem says that they are indeed equivalent. So yeah, let's maybe look at them in turn. The first condition is quite close to well-foundedness in terms of there is no infinite descending sequence, because it says whenever you have a sequence, an infinite sequence in your order Q, which you can view as a function from the natural numbers into the order, then that sequence is what you call good. And good means that there are indices I smaller than j, such that the earlier element fi in the sequence is bounded in the sense of the order by the later element fj. And if you have a linear well order, then that's indeed the case, because if you have an infinite sequence, it cannot descend forever. So by linearity, it must ascend at some point from some I to j being I plus 1, so in the next step. And for partial orders, it's quite similar, but in general, you should not demand that j is I plus 1, that this is the next element, because when you have two incomparable elements in your order, you could alternate them in your sequence, and then, well, they're incomparable, so no element will be bounded by the next one if you alternate them, but it will be bounded if you move two elements further on, and in general, you just want some earlier element to be bounded by a later one. Then the second condition is that there is indeed no infinitely descending sequence, so you have well-foundedness, and on top of that you demand that also there are no infinite antichains, so no infinite sets of incomparable elements. Then thirdly, you could think of, in the linear case, the definition of well-foundedness saying that every non-empty subset of your linear order has a minimal element. And in this case here, you don't get a single minimal element, but whenever you have a subset of your order, then you demand that there is a finite basis. So what basis means that any element in your subset has a lower bound that belongs to this basis. So it's not a unique minimal element, but you have minimal elements and you only have finitely many of them. Right? And then finally, there's a condition that makes more sense maybe when you look at partial orders that are also antisymmetric rather than general quasi-orders, because when you have such partial orders, you can think of linearizations. So they are partial, some elements might be incomparable, but you can add comparisons, and when you have added enough comparisons, maybe you have turned it into a linear order. And the condition is that however you do that, however you build your linear extension, what you get is a well order. And so this fourth condition maybe also gives some reason to think that this is the right generalization of well order from the linear to the partial context. However you linearize, you reach a well order. Now there's a small exercise proving that these are indeed equivalent. Maybe two things to say about that. First, Ramsey's theorem for pairs is useful for that. And secondly, the most difficult implication is showing that 4 implies the others. Because if you go by contraposition, then in 4, you have to build linearizations that are not well-founded. And so you have to, in particular, build some linearization. You have to add inequalities, but you have to do it in such a way that transitivity is preserved, and that's not entirely straightforward. It's not incredibly difficult either, but that's the most difficult of these directions, I would say. I didn't comment on the origin of this notion because it's somewhat complicated, and if you're interested in that, then it may be worthwhile looking at this paper of Kruskal called The Theory of Well-Quasi-Orders, a Frequently Discovered Concept. A brief remark about reverse mathematics. That's not the focus in this first part, but if you're interested in that, these equivalences that we just saw, they do not all hold over RCA0. They are not all computably true, but you can prove all of them if you have Königs lemma and a chain-anti-chain principle, and you can find the details in this paper by Cholat, Marconi, and Solomon. Okay. So why well-quasi-orderings? I mean, I would say it's a reasonably natural notion, but it's still maybe good to have some additional motivation. Please. Don't think that something is equivalent to the conjunction, but I would have to look it up. So they do have equivalences, but I guess not to the conjunction. So I'd say it's a fairly natural notion, but it's still nice to see applications. Why should we be interested in these? And I have two of them. I think this is a very nice one. So here we consider exponential polynomials with integer coefficients. So these are built like polynomials by addition and multiplication, starting with some indeterminate and integer coefficients. But then you can also take one polynomial to the power of another, and you can also iterate that and combine it with addition and multiplication. And when you close under these operations, you get the exponential polynomials. And then you can order the exponential polynomials as follows. So you view them as functions, let's say, on the natural numbers. And then you say one polynomial dominates another in the order if the corresponding function eventually, for large enough values, dominates the corresponding function of the other polynomial. And there was a question by Skolem in 1956 asking whether this order is a well order. So it's linearly ordered. It's not quite immediate, but it's something that I don't really want to comment on. For me, the main question is it well-founded or not? And this was open for close to 20 years. But then in 1973, Ehrenfeucht gave a one-page proof and published, well, with the address, it's 2 pages, the paper, a 2-page paper showing that this structure is actually well-founded. And I think that's a really nice paper. I mean, if you can write a 1 or 2-page paper, I guess that's always very nice. And I want to briefly explain how this is done. It's quite a simple trick once you know it. So the idea is that you look at some exponential polynomial, maybe take x to the x to the 2, and then you just view it as a term and view the term as a tree. So this is x times x, so you would just have maybe leaves of your tree labeled by that indeterminate x, and then they are combined by times, and then you have another leaf for this bottom x here, and then that's combined by, let's use that hat for the exponential function. So then this polynomial would correspond to this tree here. And then what Ehrenfeucht does is he just applies a theorem of Kruskal, which says that trees, finite trees, in particular with finitely many labels, form a well-quasi-order under embeddability. So whenever you have a sequence of infinitely many such trees, then some tree in the sequence can be embedded into a later tree, and you just throw it on that and learn that when you have an infinite sequence of these exponential polynomials, one of the corresponding trees will be embeddable into a later one, and then you just use, it's really quite easy, the monogenicity property of these operations to show that if the term tree can be embedded into the other term tree, then the first polynomial must be dominated by the later. Right? So it's really just finding the right application of this Kruskal theorem from the theory of well-quasi-orders, and I think that's one good motivation why it might be worth studying them. And maybe one other thing to say is that this is a well order, so it has some order type, and it's still unknown what the exact order type is. So it's somewhere between epsilon naught and the first fixed point of the epsilon function, but the precise order type is still unknown. And it's an active field of research in the sense that every once in a while there is a new paper with progress on that. And one of the most recent ones that I've seen is this one by Berarducci and Mamino, who study some fragment of this class of exponential polynomials and determine the order type of that using surreal numbers, I think. It's also quite nice because it can bring in a set of different interesting methods. But maybe that contrast is also interesting, right? They use quite specific tools, maybe from analysis number theory and so on, and the proof that it's well-founded, it's just throwing this combinatorial theorem at it. The second motivation application for well-quasi-orders is the graph-minor theorem. So I've mentioned this theorem of Kruskal about finite trees, and there's a corresponding theorem about finite graphs, which is infinitely more difficult to prove due to Robertson and Seymour, who wrote a series of about 20 papers in order to reach that theorem. And I think it's considered one of the greatest achievements in combinatorics in the last century. What the theorem says is that the class of finite graphs is well quasi-ordered under the minor relation. So minor relation means that if you want to form a minor of a graph, what you can do is you can delete some edge in the graph. This would be a minor of the graph that I drew before. You can delete some isolated vertex. In other words, you first delete the edges around it and then you delete the vertex. And then you can also contract edges. So for example, if you have, let's say, maybe this, and you contract the edge in the middle, then what that means is that you pull these 2 points together and make them into one point, and then you just attach the points that were attached before. Right? And whenever you can reach something by these operations, it's called a minor, and the minor is considered smaller in this particular order than the graph that you started with. And if you look at that order relation, then what they showed is that this is a well-quasi-ordering. Well, it's a beautiful theorem. It's also extremely important for theoretical computer science because it guarantees that some properties of graphs can be tested in polynomial time. And that comes from the third version of this definition of well-quasi-ordering, the finite basis property. Right? Because if this X is also upwards closed, then you get an equivalence, namely you get that an element is in X precisely if something in the basis can be embedded into it. An example of this is Kuratowski's theorem. So a graph is not planar precisely if the complete graph on 5 vertices or the complete bipartite graph on 3 plus 3 vertices can be embedded into it. So here we have a basis of the complement of the planar graphs consisting of two basis elements. And this relation, whether some graph is a minor of some other, that can be tested in polynomial time. So if you have a finite basis, then you can determine in polynomial time whether one of these basis elements is a minor of the graph that you want to test. And that gives you a polynomial time algorithm. What is curious is that in some cases you may not know what the algorithm actually is because you just know there is a finite basis, but you don't necessarily know what the basis elements are. But of course, on a theoretical level, it's still extremely important. And I think the first example that Robertson and Seymour themselves give is that when you have a fixed k and you're given a graph, and in that graph k pairs of vertices, then to decide whether there are k paths between these pairs of vertices that don't intersect, that can be tested in polynomial time. And that had been open, and they showed that using their theorem. It's a beautiful theorem and very important. And also, so once again, this part is not mainly about reverse mathematics, but still, it's just such a beautiful result. So reverse mathematics, Harvey-Friedman together with Robertson and Seymour showed that this graph-minor theorem cannot be proved in pi-1 comprehension. It's an extremely strong system. And I think this is really one of the most beautiful, one of the best examples for Gödel's incompleteness theorem that we have. And what I also like about it is that I think the only way we can prove that is via ordinal analysis, the only known way. So it illustrates what that method can do for you. Okay. So this is about well-quasi-orderings, and I wanted to do that in quite a lot of detail because we're really building on that, and if that is not well motivated, then it doesn't become clear why we should try and reach something better. Are there any questions about this? Oh. Any upper bound? So it's between pi1 non-comprehension and pi1 non-comprehension plus some bar induction, I think pi1 2 bar induction or so. There's a paper by Michael Rathjen and Martin Krompholz. So if you Google Rathjen and Krompholz, then I think you'll find the paper. But the precise strength, I think, is still open. You're nodding, so maybe, but I'm not sure about the history. It's also the case that, Harvey Friedman has this gap relation on embeddings of trees, and that gap relation is actually used in the proof of the Graf-Meitner theorem itself. So it's also where a concept from logic maybe came back into combinatorics and turned out to be useful there. Did you want to comment? Thanks. Yeah. Okay, so now let's try and make things better, and let's maybe first try and see why we should. So everything will be motivated by this construction here. You take a quasi-order, and you consider the power set, and you define this particular order on the power set. So you want to say when some subset of your order is bounded by another subset. And I think this is really the most natural thing. You say that one subset of the order is bounded by another if every element of the smaller set is bounded in the original order by some element of the larger set. And we will see that this operation does not preserve well-quasi-orders. So it can happen that Q is a well-quasi-ordering, but this order on the power set is not. And that will be the motivation to go towards better-quasi-orders. But let's first look at an operation that does preserve well-quasi-orders, and that's the finite power set operation. Right? So if Q is a well-quasi-order, and you can consider any sequence in this power set where all these subsets are finite, so you only look at the finite subsets, then this sequence will be good. So some element in that sequence will be bounded by a later one, and that means that the finite power set, so to speak, is a well-quasi-order. Right? So you only go out of well-quasi-orders if you start and consider infinite subsets. So yeah, let's prove that theorem. Just check how I want to write things down. Okay, so let's go by contraposition. And let's assume that this sequence is bad. And so you have finite subsets of your order. And this is bad, meaning that none of them is bounded by a later one. So if this is bad, it means, for example, that x0 is not below x1. So you have to negate that defining condition here. And what you get is there exists an element of x0 which is not bounded by any element of x1, right? So for any of the x1, x2, and so on, you can pick some x0i in x0, which is not bounded by any of the elements from xi. Is this too small or is it fine? Very good. Okay. Now the problem, as it will turn out, is that the choice you make depends on the I. But you're working with finite sets, so you can apply the pigeonhole principle to find an infinite subsequence where this x0i doesn't actually depend on the I. Right? So let's take some x0 not depending on xi, which coincides with infinitely many of these. Okay, so this holds for infinitely many I, and now we just pass to the subsequence of those i's where it holds. So by passing to a subsequence, of x1, x2, and so on. So you keep the first x0, but you pass to a subsequence of the other ones. And then you can assume that this holds for all I. So x0 is x0i for all I. And then you just consider, you just continue in the same way. So iteratively, you pick xj's from xj, which don't depend on the rest of the sequence if you thin it appropriately. Right? So you just do the same thing again and again. And then the claim is that if you now consider these lowercase xi's, which is a sequence in your original order, then this is bad. And I'll justify that in a moment, but let's maybe briefly reflect to see that this is actually the point that we wanted to reach because we are arguing by contraposition. The assumption was that Q is a well-quasi-order, so it has no bad sequences, and so if we show that this sequence is bad, then we have reached the negation of the assumption. So why is this bad? This is bad because if you have indices I smaller than j, then xi is the same as xij, because by applying the pigeonhole principle, we made them independent of the second component. But xij, by the way in which we chose it, was not bounded by anything from uppercase xj, and lowercase xj is just one of these. Okay, so that's the proof of that as a proposition. And maybe one small exercise is show that this goes through in ACA naught. So that may not be immediately clear because I iteratively picked these infinite subsequences, but you can pick them all at once by using Ramsey's theorem for 3 tuples. So that's maybe something nice to do if you haven't seen that before. Another fact about this is that there's also a reversal. This proposition is not only provable in ACA naught, it's also equivalent to ACA naught, and we will see that later. That's a result of Marcone, and we will see the proof. Okay, so here we still do have well-quasi-orders, but as I said, if you take the power set operation and admit infinite subsets as well, then you drop out of the well-quasi-orders. And there's an example for that due to Richard Rado, who looks at the two-element sets of natural numbers, and you want to write them as pairs where the first component is smaller than the second component, two-element subsets, ordered in the natural way. And then he defines some relation R on these two-element subsets, and we'll look at the definition of R in detail in a moment. And then you can verify, and we'll do that, that this relation R is a well-quasi-order on the pairs, but if you take the power set, then this is let me maybe just mention before we look at the details, because it's already in the slide, this proposition of Laver here, that example of Rado is canonical in the sense that sort of it's the only reason that for which things can fail. So whenever Q is a well-quasi-order but the power set is not, then this example of Rado will embed into the order. Now let's look at the definition. We say that one pair Mn is R smaller than another pair M prime N prime if one of the following happens. So either the first components are the same and the second components are in the usual order, arranged in the usual order on the natural numbers, or if the second component of the left pair is bounded by the first component of the right pair. Our relation also. And you can visualize this as follows. So this is taken from the PhD thesis of Gentzen, who also wrote a very nice introduction to better-quasi-orderings that I'll cite later. So I want to acknowledge where I took this picture from. This illustrates this ordering R. So what R does, first of all, these columns, they are ordered from the bottom up. But then secondly, for example, this element 0, 2, it's smaller than the element 3, 4, I guess, because the second component 2 is smaller than the first component 3. That's what these now we should check that this is a well-quasi-ordering, but that the power set is no longer well-quasi-ordered. And let's do that. So the first case is that some of these MIs of the first components becomes larger than this single number n0. So MI becomes larger than n0 for some I. And maybe I actually want to write it the other way around. So n0 is smaller than MI. And because then you immediately see, this is the second clause here in the definition. The second component here is smaller than the first component of some other pair. So then the pair M0, N0 will be R below the pair Ni, Mi for that reason. And the second case is all the MIs are bounded by N0. But then again, by the pigeonhole principle, so there are only finitely many possibilities below N0, so you may as well assume that they are all the same. So that also already gives us one part of this first disjunct here. The first components are now always the same. But then the second components cannot descend forever, so we must also have this inequality in the second components at some point, right? So we must have that Ni is bounded by Ni plus 1 for some I, and then this pair here is R below the next pair. not necessarily the same, the next pair in the original sequence, because we have thinned the original sequence when we applied the pigeonhole principle, but bounded by some later pair. Shall we switch to the other microphone? Yes. Yeah, let's try and do that. Thanks. Is that still okay? Yeah, that works. Thanks. Thanks a lot. Okay. So this R is a well-quasi-ordering, but I claim that when you take the power set, then you don't have a well-quasi-ordering anymore. So the claim is that if you take the power set of pairs with these R relation, then this is not a well-quasi-order. And to show that it's not a well-quasi-order, we should show that there's a bad sequence, so some sequence where no element is dominated by a later one. And the bad sequence simply consists of the columns. Yeah? So we take xi to be the pairs ij, where j, well, in all these pairs the second component is later than the first component, and we take those that have first component I. And so the gray set that you see here, this set called D3, is the downward closure of one of the columns, right? So this order on the power set becomes somewhat nicer if you only consider downward closed sets rather than arbitrary subsets. So that's why he took this downward closure and put the gray set, but for the tutorial I wanted to take just the usual power set. Right. And the claim is that this is bad, so xi is not below, in this power set order, xj for I smaller than j. And in fact, the two are incomparable, so you have an infinite anti-chain. But let's just show this non-equality here. So what do you have to do to show the non-inequality? So the definition of the inequality was this inequality would hold if everything in here, for everything in here, you would find something in here that dominates it. So to show that the inequality does not hold, you have to find something in here that is not dominated by anything in here. And the element that you can take is the pair ij, right, which is in xi. And the claim is that this is not dominated by anything in xj, and the things in xj are pairs with first component j and second component k. And none of these dominate the pair ij. And why is that? Well, if the inequality would hold, then one of these two cases would have to apply. In the first case, the two first components would have to be equal, but they are not because I is smaller than j. And in the second case, sorry about that, the second component of the left pair would have to be strictly smaller than the first component of the right pair, so j would have to be strictly smaller than j, which of course is not the case. Okay. So that shows that this infinitary power set operation does not preserve well-quasi-orderings. And in general, the slogan is that well-quasi-orderings have good closure properties under finitary operations, but not under infinity operations. And the better-quasi-orderings that we are going to see have also good closure properties under infinity operations, and that's what they were made for. So, yeah, please interrupt at any point. Otherwise, we can now really approach the definition of better-quasi-orderings. And maybe the crucial step is this proposition here. So the idea is we want to repair the theorem, and we want to somehow ensure that the full power set with all the infinite subsets of Q becomes a well-quasi-order. And to do that, we somehow have to strengthen the assumption. So we have to assume more than that Q is a well-quasi-order. And the idea is that we can consider something like generalized sequences. So sequences would be functions from the natural numbers into Q, or in other words, maybe from singletons of natural numbers into Q, and rather than singletons, we now consider a sequence that has as a domain of definition all the pairs of natural numbers. Right. And the pairs of natural numbers you want to order as follows with this triangle relation. So once again, the first component m of a pair is always smaller than the second component n of a pair. And the definition is that you have this triangle relation if the two pairs overlap in the sense that this second component n coincides with this first component k. So, for example, you would have 1, 3 is in triangle relation with 3, 27 because these two components overlap. Right? Okay. And then the proposition is that if any generalized sequence with these pairs as domains is good, in the sense that you can find a triangle relation between one pair S and another pair T, such that the value on S is bounded by the value on T. If this holds, then we get what we want, namely the power set is a well-quasi-order. And it also turns out that this is not just a sufficient condition, but actually that you get an equivalence, so the converse holds as well. If the power set of Q is a well-quasi-order, then all such generalized sequences will be good. So that's what I want to show next. And then we'll see if I can put a full definition of better-quasi-orders on the slides now or after the coffee break. But we'll see that. So let's just do the same as before. We want to show that the power set of Q is a well-quasi-order. So let's again go by contraposition and assume that it's not a well-quasi-order, so that we have a bad sequence. And then we do exactly the same as before. So for I smaller than j, if the sequence is bad, xi is not below xj. So that means it's not the case that everything in xi is dominated by something in xj. So we find something in xi which is dominated by nothing in xj, and we pick these elements. So we pick, and now we just call it fij in xi, such that this thing we picked is not below any y in xj. Right? We picked something from xi that's not below anything xj, and that witnesses that the sequence is bad. So it's really the same as before, except that now I called it f of I and j rather than x with index ij. It's exactly the same otherwise, except for the notational difference. And the other difference is, so previously we said, okay, well, it's annoying that this thing depends on the second component j and not just on this I that we are looking at right now. So let's apply the pigeonhole principle to get rid of this dependency. And now the crucial idea is that we just don't do it, right? We can't do it here, so we just accept that there's this dependency on j as well. Okay. And now I claim that this completes the proof of the contraposition in the sense that this f is one that violates the assumption, namely fij is not bounded by fjk because fjk is something from xj, right? And it's not bounded by anything from xj. And this is true whenever ij is triangle smaller than jk, right? So whenever these two j's are the same. There are no S triangles smaller than t such that we would have an inequality. And then let's maybe look at the converse as well. So conversely, we now prove the contraposition of the other direction, so we assume that f is bad. And we want to show that in this case, the power set is not well quasi-ordered. So to witness that it's not well quasi-ordered, we have to pick an infinite sequence, which is not good. So what we do is the ith set xi in this infinite sequence is just the ith row of f, so to speak, the ith column. So you take fij, the values for all the j's that you can put, namely those that are bigger than I. Okay. And now we want to show that this sequence is actually bad. So let's assume otherwise. I think I could probably eliminate some of the contrapositions and proofs by contradiction right now, but anyway. We want to show that this sequence here is bad. So if that was not the case, so if there were I smaller than j, such that xi was bounded by xj, then everything in xi has to be dominated by something in xj, and so in particular, the value fij, which lies in xi, would have to be dominated by some y in xj. Yeah? But y is in xj, so by definition, all the things in xj are values of f on a pair with first component j. And that would contradict the assumption that f is bad, because now, where do I put this? Maybe just in the last line down here. Sorry about this. Now, ij is triangle smaller than jk. And also here we had that fij is bounded by y, which is fjk. And that would witness that f is good, right? We have found two things that are in the triangle relation such that the values are in the order relation. Okay, so the end was maybe a bit confused, sorry about that. But we have this equivalence, and actually it's really straightforward. There's no idea in this proof, right? You just shake the definitions a little bit. And what we have really done, I think, is move the complexity from the order, so from the range of f, so to speak, into the domain of f. We can just move it between the range and the domain. Yeah, so in the final 5 minutes, let me just start with the general definition of better-quasi-orderings, and then maybe I'll repeat it at the beginning of the second lecture. I think it's maybe even good to hear it twice. So now we generalize. We've just considered the two-element sets of natural numbers, and now we have this notation that we've seen before, all the finite subsets of natural numbers, and you should think of all of these finite subsets as strictly increasing sequences that enumerate these sets. And then here you have the infinite subsets of natural numbers, which you can think of as infinite strictly increasing sequences. And then you have this notation here, so this means that S is a strict initial segment of T. So T starts with the sequence S, but then continues. And we use, because we can also view these sequences as sets, so we can also use the usual set-theoretic notation for strict containment of sets. You always order sets in strictly increasing order. What do you mean by that? So, no, what that means is that, for example, 1, 3 would be a strict subset of 1, 2, 3, but not an initial segment. Right? Does that make sense? 3, 1 doesn't exist. You just write things in increasing order always. So S and T are in strictly increasing order. Yes. Yeah, all sequences of natural numbers are. They are. You just identify sets and they're strictly increasing enumerations. And then you have this notion of block here. So you should think of a block as the leaves of a well-founded tree, or maybe not as the leaves, but rather as the things that are just outside of the tree. Right? And formally, a block is a set of finite sequences such that any infinite sequence has an initial segment in that set, and also the block does not contain two comparable sequences. So no sequence in the block is a strict initial segment of another sequence in the block. Right? But let's maybe draw that picture. So you have a well-founded tree with the empty sequence at the root. And then let's maybe say it contains the sequence singleton sequence 1, but maybe not the singleton sequence 0, just leave that out. And it contains the singleton sequence 2, some of these, and then maybe it doesn't contain anything up here, but maybe it contains some of the extensions of the singleton sequence 2 and so on, and this is a well-founded tree, and the block consists of all the things that are just outside of the tree. So here the singleton sequence 0 is just outside of the tree, and here above 1 we have all the extensions of the singleton sequence 1, and here we have 2, 4, because I didn't put it in the tree, but then these are in the tree, and then the block B will collect all these pink things, all the things that are just outside of the well-founded tree. So for every branch of the full tree, you would just check where it runs out of the tree, which must happen because it's well-founded, and then you will put the first thing where it runs out of the tree inside your block. And that's also why two things are incomparable, because you just put the first thing where your branch runs outside of the tree. Yeah, so these are blocks. And then there is also the notion of barrier, which I want to mention briefly. So if you strengthen that second condition, the block doesn't contain a sequence and a strict extension of that sequence. If you strengthen that into the block doesn't even contain one sequence and some other sequence that enumerates a superset of its elements, then you call that a barrier. And personally, I'd say that the notion of block seems more natural to me, but sometimes for technical reasons, it's quite important to consider these barriers. And for the course, I'll just ignore the difference. And this is justified to some extent because Marcone has shown, or maybe it was shown in this joint paper with Jolak and Solomon, I'm not quite sure, that the following definitions are equivalent, at least over Königs lemma, no matter if you take blocks or barriers. And so just want to ignore that difference. And an example, so the following are blocks and even barriers, all the two-element subsets of the natural numbers, so the domain of definition that we have seen in this previous proposition here, and then something called the Schreier barrier. So you take all the sequences such that the length of the sequence is the minimal element of the sequence plus one. Yeah, so you can also check that this is a barrier. And maybe seeing this first condition is easy enough, because if you have an infinite subset of the natural numbers, you just look at the smallest element of that infinite set. That's this minimum here. Minimum plus one is some number. And then the initial segment of this x will just be the one that has this length. So you take your infinite set and you just take the initial segment that is as long as the first element of that set is large. Yeah, so these are blocks. Okay, and then maybe I'll stop here because I think it's time for the coffee break.